So it's been wonderful, and I'm very grateful to the organizers for the invitation. So my first Beyond Uniform Hyperbolicity conference was in 2006. So I'm kind of feeling old here. But I'm glad to see so many young people. So I'm speaking about solenoidal surfaces of finite type and their horocycle flows. So if you don't know what a solenoidal surface is, you're good, okay? But you probably know what a surface is. So a hyperbolic surface, the geodesic flow of the hyperbolic surface is an example of a dynamical system you've all been acquainted with. It was studied by Poincaré and Adamart, who focused mainly on the study of the periodic orbits, and then was famously studied by Hopf. And this particular example is a setting which gave rise to the Hopf argument. And it's an Nosov flow, as you probably know. So the study of the geodesic flow in a hyperbolic surface is also the study of the horocycle flow, so you can't have without the other. The horocycle flows, which I'll call H plus and H minus, parameterize the curves which are tangent to the strong stable and unstrong stable distributions for the geodesic flow. So you're probably familiar with the picture below, which is the hyperbolic plane. So here you have the a green vector v, and then the geodesic trajectory for v, which is in the unit tangent bundle, and this is the notation I will be using, unit tangent bundle to hyperbolic plane. The yellow line is a geodesic orbit, and the red line is a horocycle orbit. That is this set of points and vectors, okay? And that would be the stable horocycle I have depicted there, and I'll be working with the stable horocycle flow throughout. So what do we know about the dynamics of the stable horocycle flow in surfaces, in hyperbolic surfaces of finite area? Well, we know many things. The first thing we know is this very important theorem. This theorem by Hedlund, which is very important, but which will be particularly important for us today, that describes all orbit closures. It says that for a hyperbolic surface of finite area, orbits are dense or closed, periodic, and periodic orbits are associated to cusps in the surface. So each cusp is endowed with a one-parameter family of closed orbits for the horocycle flow. The next result, which we know, is Furstenberg's theorem that says that for a compact hyperbolic surface, the horocycle flow is uniquely ergodic. The unique ergodic measure being the Lebesgue measure on the unit tangent bundle, which is also called, or usually called, the Liouville measure. We also know an ergodic analog of Hedlund's theorem, which is the complete description of ergodic measures for the horocycle flow on these surfaces. So it's due to Danny for the modular orbifold and to Danny and Smiley for all hyperbolic surfaces of finite type. And they prove that the only ergodic measures for the horocycle flow are Liouville measure in the unit tangent bundle to S, and the measures supported by periodic orbits. And then we have this theorem by Peter Sarnak, which will also be very important for us today, that says the following. So this is, you have to think of the unit tangent bundle to the surface. which is a phase space for the horocycle flow, and then you have a closed horocycle orbit and the associated ergodic measure mu. So if you push a horocycle orbit under the geodesic flow, you get another horocycle orbit. So since these are stable horocycles, if you push this under the geodesic flow for positive times, you're going more and more into the cusp. But if you push it under negative times of the geodesic flow, you're going more and more towards the surface. So eventually, when you push this red curve enough, and its associated ergodic measure enough, it goes around the surface in some way, which is, of course, always freely homotopic to the original curve. So you have to think of the probability supported in this curve, which gets longer and longer as you push it with the geodesic flow for negative times. And what Sarnak proved is that these measures, which are the push forwards under the geodesic flow for negative times of the ergodic measure supported on this orbit, converge to Liouville measure on the unit tangent bundle. And this is also a theorem which will be important for us today. Well, then, of course, there's another description of the geodesic flow on a surface in terms of homogeneous dynamics. So a hyperbolic surface is a quotient of the hyperbolic plane under the action of a Fuchsian group. And this group is a discrete subgroup of, no, oops, what am I doing? Wait. No, okay. This is a subgroup of PSL2ER, which is the group of orientation-preserving isometries of the hyperbolic plane, and the surface is simply the quotient of the hyperbolic plane under a Fuchsian group, and the unit tangent bundle can be identified to the quotient of PSL2R under the action of gamma. And this admits a right action of the group PSL2R. It's a right transitive action of PSL2R, okay? So this is the quotient under the PSL2R under the left action by translations of this subgroup, and it admits the action of right multiplication by elements of PSL2R. So if you look at the action of this particular subgroup of PSL2R, you're looking at the geodesic flow on the hyperbolic surface. And if you look at the action of this particular subgroup, or the unipotent subgroup, you're looking at the horocycle flow. So then, of course, if you see it in this way, it's the number 0 example in Ratner's theory. Okay, so by the 1990s, most of what you could ask about the horocycle flow in hyperbolic surface is a finite area. Well, Ratner's theorem would answer that for you, okay? So what do we know for surfaces of infinite area? It gets trickier. So if you have a hyperbolic surface of infinite area, if it's geometrically finite, which is the same as having a finitely generated fundamental group, then people understand stuff, okay? So people understand orbit closures, people understand the invariant measures, and so on. And by people, I mean those people and others. But when you move onto the realm of geometrically infinite hyperbolic surfaces, you're in very, very wild territory. And many people have understood stuff, but mostly orbit closures or invariant measures are not fully understood. So describing orbit closures for the horocycle flow in geometrically infinite hyperbolic surfaces is a problem which is pretty much wide open, okay? Well, no, that's not definition. So definition is a fundamental polygon has infinitely many sides, but in dimension 2, that's the same as having a fundamental group which is not finitely generated. Yeah. So, and this is very, very wild territory. So that's not what I was speaking about, but just I wanted to say that understanding horocycle orbit closures in other settings always carries this difficulty that we don't fully understand them for surfaces, okay? So I'll be speaking about joint work with Fernando Alcalde Cuesta, Álvaro Carballido Costas from Santiago de Compostela in Spain, and with Alberto Berkowski sitting right here, who you all know. So we're studying the horocycle flow on hyperbolic solenoidal surfaces of finite type. So what is this? So a hyperbolic solenoidal surface is, first of all, what is a solenoidal surface? Well, it's a foliated space, okay, or a lamination. It's a space, a matricial space, which is foliated with a foliation of dimension 2, and it's transversely canted. So it's a space which is locally a two-dimensional disk times the cantor set. And then what does it mean for it to be hyperbolic? It means that you have, along the leaves, hyperbolic metrics. And when you vary along the transverse directions, these metrics move continuously. So that's a hyperbolic solenoidal surface. And what does it mean? What does a finite type mean? Well, it's a very specific example. So we have a hyperbolic solenoidal surface, which is of the following kind. Take a hyperbolic surface of finite area. And then you have a fiber bundle, X fibers over S naught. And the fiber is a cantor set. This fiber is transferred to the foliated structure. And then the hyperbolic metric here is simply the pullback under pi of the metric on S naught. So this is the creature. You have the base, which is a solenoidal surface, sorry, a hyperbolic surface of finite area. And then you have this X thing that locally is a disk times a cantor space. So here an open set in S naught will be lifted to like a deck of cards, a transversal cantor deck of cards. And the hyperbolic metric here, well, you just copy it on each one of these. So that's the creature. And then, well, if we call if G is PSL2R, the unit tangent bundle to this space, that is simply defined by you take unit tangent vectors here. So along the only direction which is differentiable, so you can take vectors there. And that would be the unit tangent space, and the unit tangent space is a G space. So it has a PSL2R action, for which the orbits are the leaves in this unit tangent space. And you also have the geodesic and the horocycle flows given as actions of one-parameter subgroups of PSL2R, okay? So you're not necessarily in the setting of homogeneous dynamics because the whole space is not a priori homogeneous. It's locally PSL2R times cantor set, but you still have this very, very nice Lie group actions with very fine properties, okay? So then the fibration from the unit tangent bundle to the hyperbolic solenoidal surface to the unit tangent bundle to the base surface sends geodesics onto geodesics, horocycle onto horocycle, because at the level of plugs, you have isometries, okay? Yeah, I'll come to this. I'll come to this. So I'm going to say what motivated us to do this. Okay. So, okay. So the question I would like to address is what kind of compact invariant sets for the horocycle flow do you have in these creatures, okay? And first of all, a remark, there exist compact invariant sets for the horocycle flow. Because if you take your surface in the base here, you take a closed orbit for the horocycle flow, its preimage under the fibration will give you a compact invariant set under the horocycle flow because the projection is proper, okay? So this question makes sense because there exist compact invariant sets. And in fact, we have the following. So take the Cantor set, the Cantor set, and your favorite homeomorphism of the Cantor set, okay? Now, take the suspension of this homeomorphism, and I can give you a hyperbolic solenoidal surface of finite type that has this flow, which is a suspension of your favorite homeomorphism of the Cantor set, embedded as an invariant set for the horocycle flow. Okay, so this, of course, the suspension of a homeomorphism of the Cantor set will give you a one-dimensional lamination, which is transversely Cantor. And you can embed this, so what I'm saying is you can embed this one-dimensional lamination, which is transversely Cantor, into the unit tangent bundle of the solenoidal surface, of one solenoidal surface of finite type, as a minimal set for the horocycle flow. That is to say, a compact invariant set for the horocycle flow in this setting can't really be anything because everyone's favorite dynamical system admits an extension to a homeomorphism of the Cantor set. So this is really anything. And what this says is, this question, what kind of compact invariant sets can appear in the unit tangent bundle to a surface like this? Well, this question makes no sense if you want to answer it in any meaningful way unless you put some additional assumptions, okay? So, and that I'm coming to Andres' question, we're going to focus on some subclass of these surfaces, and it's some subclass which we like. It has some important and beautiful examples, and I'll be more precise in a minute. So the subclass is the following. You start with one hyperbolic surface, a finite area, and you take a finite cover of it, a finite covering, and then another one, and then another one, and then another one, and so on and so forth. And you construct the inverse limit of this tower of finite coverings. So if you haven't seen the inverse limit construction, it's the following. It's something very similar to a space of pre-orbits of an endomorphism, okay? So you take all sequences where each xn belongs to the surface Sn at the nth level in such a way that when you take the first covering, this point goes onto this one. When you take the second one, this one goes onto this one, etc. So namely, a point here is you take some point in S naught, and you take one preimage under P naught, and for this preimage you get one preimage under P1, and so on, with the product topology. Okay. These are not branch covers because, well, if we take our solenoidal surface of finite area, we have removed the cusp. If you compactify it, you have branch coverings, and it's the exact same topological information. So you can think it, and okay. So, okay. When the coverings are Galois coverings, you have some additional structure. You get, in the transverse Cantor set, you get also a group structure. So in this case, the solenoidal surface you get at the inverse limit is actually homogeneous. So you could do Ratner's theory here. So normally Ratner's theory would apply to tell you what the horocycle orbit closures are. The thing is, it's very difficult to pull this off in specific examples, okay? So it's not practical to do so, okay? But it's possible. So why did we go down this particular rabbit hole? That's the answer to your question. So what's the one example we love? It's the inverse limit of all finite regular coverings of the sphere minus 3 points. And why do we love this example? Because of this beautiful, I know how to say text because it's not really a paper, well, paper by Grothendieck from the year 1984, a sketch of a program. So here Grothendieck explains many ideas which were the basis for a lot of beautiful mathematics. And he has this incredible insight that thinking about the inverse limit of all coverings of the projective line minus 3 points gives you a way of thinking about the fundamental group, which is the correct way if you want to generalize it over for curves over number fields, okay? So this is in the origin of the definition of the algebraic fundamental group, also known as étale fundamental group. So this beautiful object, which is this inverse limit of the Riemann sphere in our case, minus 3 points, has transversally all the information about all finite coverings of the sphere. So all the topological information is there, and in the tangent direction, you have all the information about the conformal structure, which is, of course, also a hyperbolic structure. So this is really a very beautiful object, and it's the one example we love, and our theorems do apply to this example, okay? So here is some words to the huge influence of Grothendieck's work. Here you can see this beautiful paper by Deligne called the fundamental group of the projective line minus 3 points, which is a very funny title. Okay, so so what did we prove for this specific family of hyperbolic solenoidal surfaces of finite type? So now I'm really focusing on this family, which is obtained as inverse limit of, let's say, regular coverings of surfaces, regular finite coverings of surfaces, okay? So remember Hedlund's theorem for one surface that said that in one hyperbolic surface of finite area, every orbit of the horocycle flow was either dense or periodic. So what we prove is that in this setting, every horocycle orbit is either dense or projects onto a periodic orbit in the original surface, in the surface on the bottom of the tower of coverings, okay? So if we want to answer the question of what are the compact invariant sets under the horocycle flow, all we have to understand is what are the sets. You have here your hyperbolic solenoidal surface. Well, its unit tangent bundle. It projects onto the unit tangent bundle of the base surface. You have a closed horocycle orbit here, and all you need to know is what lies above it. Those are all that will give you all the compact sets, invariant sets, okay? So, we described these things. This theorem is stated not assuming the coverings are regular. So if you have a hyperbolic surface of finite area and the inverse limits of finite coverings of S naught, and you have a closed horocycle orbit inside the unit tangent bundle to S naught, so a closed orbit just turning around a cusp here, what does it preimage under the projection from the unit tangent bundle to this, to the unit tangent bundle to this, look like? Well, this guy is a compact set which is invariant under the horocycle flow, of course, but it's not just any old compact set. First of all, it's a disjoint union of minimal sets. So every orbit closure for the horocycle flow, unless the orbit is dense, is a minimal set. And then this union of minimal sets can be a finite union or an uncountable union. And that's what you get. So all these cases can be realized. So if you want a horocycle orbit on S naught that lifts to the disjoint union of 8 minimal sets, I can give you 8, okay? So, and then, well, when you have finitely many minimal sets on top of a single orbit, all these sets are going to be one-dimensional solenoids. So they're going to be one-dimensional and decomposable continua, okay? That's what you're getting. And if you have uncountably many, you can either have uncountably many periodic orbits for the horocycle flow in the solenoidal surface, or uncountably many one-dimensional solenoids. All this sitting on top of a single periodic orbit on the base surface. Okay, oops. So, and then we ask ourselves, well, what happens to these minimal sets when you push them with the geodesic flow? So when you push them, since we're looking at the stable horocycle flow, when you push them with positive times of the geodesic flow, you go to the ends of the hyperbolic solenoidal surface. But when you push them for negative times of the geodesic flow, like Sarnak did, we proved that you're converging to everything in the following sense. If you take the end compactification of the unit tangent bundle to the hyperbolic solenoidal surface, then every minimal set, when pushed under the geodesic flow for negative times, converges to the whole space in the house of topology. Okay, so one thing we have still to look at is what happens to measures. So can you do this measure theoretically? So I'm not sketching the proof of any of these results. I'd just like to focus on some examples to give you a flavor of what the dynamics of the horocycle flow in these things look like. So, house of topology? Well, no, it doesn't matter. So you have the hyperbolic metrical on the leaves, and then no, not really. So the fiber is compact, it won't make a difference, but you do have to choose one. Okay. So what I wanted was to show you some examples of these objects to give you a flavor of what they are like. So the first example I present is you have a closed horocycle orbit, and on top of it, you have uncountably many one-dimensional solenoids, which are minimal for the horocycle flow. Okay? So we start by looking at a very classical object. So take the group SL2C and the morphism that sends this to SL2C mod NC, which is simply you take a matrix of integer coefficients, A, B, C, D, and you mod n all the coefficients, okay? So this is a morphism of group, and it's surjective. So if you take the kernel of this morphism called gamma n, this is called the principal congress group of a level n, and it's of course a normal subgroup of SL2C. So we can consider the hyperbolic surface, which is a quotient of the hyperbolic plane under the action of this function group, okay? So if you get sigma 1 will simply be the modular orbifold. But, well, a fact of life is, so these groups can have some elliptic elements, but they don't for n greater or equal to 3, so the sigma n are surfaces. And then, well, there are many known facts, okay? The first known fact is that this is normal here, of course, because it's a kernel of something, okay? And so this means that this surface sigma n covers a modular orbifold, and it's a Galois covering. And also, if you have not every two surfaces of this one are one a covering of the other, but if you look at the definition of these groups, you'll see that if n divides m, then sigma n covers sigma n. So we have a big family of finite Galois coverings of hyperbolic surfaces, and many quite famous hyperbolic surfaces appear in this family, as a matter of fact, okay? Well, then other things people know, they know how many sheets this covering has because people have computed the index of this subgroup in this group, okay? So it's just a number, but this is the number of sheets that the covering sigma n, sigma 1 has, and all I want to do is focus on this. This is Euler's totem function. So this is positive, so this is positive, all this is positive. So this is something like n squared. Sigma 1 is the modular orbifold, so I have it here, this. Sigma 1 is a quotient of the hyperbolic plane under the action of PSL2C. Yeah. No. It's okay because it's, so this is, Sigma 1. So I don't know if I got the end right, but what I mean is all these are coverings. So these guys, oh, wait a minute. So these guys are subgroups of, these guys are subgroups of SL2C. So it's so these surfaces are coverings of the modular surface. Okay. And the modular surface has one cusp, so that's what it's nice from our point of view. And so you can know how many sheets this covering has and so on. So what I want to point out is that, never mind the actual number, okay? And also, we know how many cusps this surface has, okay? So the number of cusps it has is the number of sheets divided by n. So what's important in this example is that sigma n is a finite covering of the modular surface of this number of cusps, and each cusp projects n to 1 onto the unique cusp of the modular surface. That's what is important. And the number of cusps goes to infinity with n, and the number of cusps of sigma n projects n to 1. So these surfaces sigma n have more and more cusps as n grows, and they all project with multiplicity. So if you want to think of these coverings as ramified coverings, the compactification of the cusps will be branch points, okay? So, well, we're going to take the inverse limit. So since I defined it for a tower of coverings, I'll take a tower. So I choose a subfamily. I choose a subfamily of these surfaces so as to have the coverings in a tower, okay? And I take the inverse limit. And then, as before, its unit tangent bundle fibers over the unit tangent bundle of the modular surface with fiber a Cantor set. So if I take a closed horocycle turning once around the cusp of the modular surface, what do I see above it? That's the question. And the answer is, I see uncountably many connected components, each of which is a one-dimensional solenoid. So what I see above the horocycle, the closed horocycle in the modular surface, is a disjoint union of uncountably many minimal sets for the horocycle flow, each of which is a one-dimensional solenoid, okay? So you can do simpler examples. So this one, for instance, is an example where you have one closed horocycle in the surface on the base, and what you see above is only one solenoid, okay? So this is the tower of coverings. I start with this surface here, and H is the closed horocycle associated to this cusp, and I take a 2-to-1 covering that does this. Let's say it turns twice around this guy, identifying this handle with this handle, okay? And then a covering of this one, which turns twice around this cusp, identifying these two handles, which these two handles, and the same with this, okay? Well, sorry, identifying this with this, and so on and so forth. So I can go backwards, okay? So these covers are regular because they're 2-to-1. And what's the dynamics on top of this curve? Well, here I take the 2-to-1 covering, then I take a 2 to 1 covering, then I take a 2 to 1 covering. So in the inverse limit, this is the dyadic solenoid. So this gives a closed, so over this particular red horocycle orbit, in the limit, I see one connected component, which is a minimal set for the horocycle flow, which is the dyadic solenoid, okay? Yes? Yeah. Well, I mean, if you have to think of the vectors on top of this that make of it a periodic orbit, and then you do all the thing. So it is a curve. It's not the curve on the surface, it's a curve on the unit tangent. And then that's what you're seeing. So yeah, if you want to think of the limit thing as a suspension, it's what you're saying. The monodromy of this curve on top is C goes to C2. So it's it's the expanding map of the U2 in the country. Yeah. Yeah. Okay. Yes. So this will give you one connected component. You can have another solenoid on top of this. And then, for instance, this is another example where on top of one closed horocycle, you'll see uncountably many closed orbits for the horocycle. And it's very simple. I start with this surface. Oh, this is not, okay. So this is a cyclic covering, which in my drawing is 4 to 1. Okay, so you have to imagine the curve around this handle opening 4 times, okay? So the covering of the surface is 4 to 1, which means that each cusp goes to this one, but each cusp goes 1 to 1 onto the cusp here. So for the red curves, the covering is 1 to 1, okay? And then here I made it 4 to 1 again, the covering of the surface, so I have 8 cusps here, and each one goes 1 to 1 onto here, and here it goes 1 to 1 onto here. So this is 2 to 1 over this, say, okay? And well, so in the end, this red curves is being opened to, say, a Cantor set of curves. So in the inverse limit, I'll have uncountably many red curves, but they will all be closed orbits for the horocycle flow. So if you wanted to have an example where over one closed horocycle you had, say, 23 connected components, you could do a combination of this example and this example. So you do this to get, say, 23, and then you do this to get solenoids on top of each other, 23, and things like that. So all the possibilities in the theorem that we had that described what you see on top of a single horocycle are realized. So that's it. Thank you.
Thank you, Matilde. Are there any questions? I was curious, for the small, like sigma 2, sigma 3, what do the orbifolds look like? Do you know offhand?
Alberto knows them all by heart. Infinitely many, and he knows them all by heart, but sigma 7 is the Klein quartic, for instance. There are other famous curves in this, surfaces in this. Yeah, there's one that has genus 0 and 20 cusps, which is the yes, when you divide the hyperbolic plane and the principal congruence groups.
Finite number of surface of a cubic genus.
Finite, yeah, okay.
I don't remember the number. It's a theorem of.
But,
I'm a little deaf, so that was the question.
So the question was, what well-known surfaces appear in this family of, when you quotient the hyperbolic plane under the principal congruence groups. So for 7, you get the plane quartic, don't you?
Yeah, you get a clay quartic. Otherwise, you get a icosahedra vertices.
Okay,
Yeah,
nice.
beautiful, and has to do with
That's for 3, isn't it?
the modular wiles, etc. No? Modular curves.
Yes.
But I don't
Okay,
remember
nice. All right, other questions? All right, well, please join me in thanking Matilde again.